All right, well, there we go. Another live stream in the middle of the day, out of my usual comfort zone and without a very concrete plan. Let me share my screen, and I see Steve is here on the chat. So, hi, Steve. Nice to meet you. And by the way, thank you for helping out with spotting the issue on Safari. And this time I decided to, just a moment, yeah. So I decided to open an issue for all the stuff that we, all the things that we need to do instead of, just managing those in a text file. So we can remove those from the text file. Thanks for the feedback about the audio. So these are gone. We have issues for them now. But I think the most interesting stuff that happened since the last scheduled stream is that we tried to debug SysTick, the ARM system timer, and it went horribly wrong. And one nice guy named Valerio, and you may remember his name from the chat and also from a pull request that he sent before the previous stream. He opened this issue. Where is that? Yes, this one. He continued debugging SysTick and tried to figure out why it behaves the way it does, or why it misbehaves. And eventually he stumbled upon this warning about an unimplemented instruction in place where there should have been an instruction. And we ping-ponged about that and debugged it, and we found out that so when GDB sets a breakpoint, it it replaces the instruction at a breakpoint location with this UDF instruction, and this is something we implemented at pretty much at the beginning when we started working about the GDB implementation. But this instruction, this UDF instruction, has two possible encoding. Hey Valerio, good to see you here on the stream as well. So it has this UDF IMM8, but there is also UDF.W IMM16, and we haven't implemented that one. So whenever GDB used that instruction, and I'm not sure what causes GDB to prefer one over the other. Maybe when we are overriding 4-byte instruction like BL, it uses this one. I'm not sure, but whenever it does, two things happen. First of all, it misses the breakpoint because our code can't decode this. And then the second thing that happens is the second byte is A000, which translates to add R0 PC 0, which means that R0 is going to get the value of PC, and then things probably go wrong from that point. So I remember seeing some weird behavior when you tried to debug the program in the past, and it would go crazy and it wouldn't stop in breakpoints and finish wouldn't work. So hopefully fixing this will help us get better debugging experience, finally debugging experience that is more stable and reliable. So we'll start with that, and then I went over the datasheet and made a list of all the instructions that we still don't implement. And apparently there are like, so these are like hints that aren't really important, except for the fact that those instructions are 2-byte instruction, and then a 2-word instruction, 32 bits. And then the second part of this instruction may confuse the or emulator, but I find it interesting that there are like 1, 2, 3, 4, 5 instructions that are they seem to be arithmetic instructions, but we haven't encountered them yet. And it's not like the ARM M6 has a huge list of instructions. It has like I think about 77 instructions, and it's interesting to see that all those instructions that are those 5 arithmetic instructions aren't really used. But in any case, we are going to implement them just so we won't get hit by that in the future. And then there are like this wait for interrupt and yield, which we'll probably decode them but not implement them at the moment, just like DSB, ISB. All right, and other than that, we also wanted to set up ESLint, not urgent, but it would have figured that it would have prevented that stupid bug. So that's also a cool thing to do. And we have this one, which, I mean, we found out this last time that this is probably buggy, so we will take a look at that. But first of all, let's fix this one, because this means we will probably finally get a good, stable debugging experience. So yeah, and thank you, Valeria, so much for finding a way to reproduce this and uploading the ELF and the hex files that you used. It was super useful. Like I think you wrote it to me on the chat. It took me 5 minutes since once I had this issue with all the information to reproduce this, and then a few more minutes to pinpoint this bug. So that's really that was really efficient. Okay. Let's get down to coding. So the first thing we want to do is, like always, we're going to encode this opcode UDF. We don't have UDF yet, so assembler. Yeah, let's add both variants if we are at it already. Why do I have this other window? Okay, I want this spec file. So export function opcode UDF, and this one gets we have the encoding though, UDF.W, because that's the second variant for now. So this is the expected encoding. So let's add a test case UDF.W 0. All right, opcode UDF with 0 should equal this. I think this is going to be the high byte, right? Always have like that problem when I'm not sure how it works with anyway, we'll try and see. All right, IMM16 number, and then we return. So yeah, let's go to the datasheet where we can copy paste stuff. UDF. So this is like the higher, the lower 12 bits, and then the higher, okay, I'll just add a 1. All right, so then we can split it for is IMM16, and then we take the lower bits, and then const IMM12 is just IMM16, and we take the lower 12 bits, and then we have this. So shifted by 16 to 20, or IMM4 by 16, or this by 12, or IMM12. Okay, that looks okay. Let's see if the test case passes. Oh, we already imported, so it doesn't. Yeah, and then where is the part that we make sure it's not negative? Do we do this in the tests, or I guess we will do it in the encoding? So this is shifted just to make sure the result is always positive. Okay, still not happy, so I guess we have to swap those. Yeah, now it's happy. Now just need to make sure this is still like encoding it correctly. We'll do it in a moment. Let's first write the, and then I think we like to have the code here and the test on the left, P2040 spec, yeah. And then I think we already have a test case for UDF, so UDF.W 0 T2 encoding. So in this case, how do you do it with set you into 32? Okay, cool. UDF. So I wanted to see for 32 bits opcodes, what's the way to go? Opcode UDF2, and then R0, no, just 0, and then we expect it to call on break and to call this with 0. And obviously this fails because we haven't done it. And if we focus on this test, I think we should also see, interesting, it doesn't say we executed an invalid instruction. I expected it to do it, but no. So maybe the encoding is incorrect after all. Let's see what it does instead. Anything green? Or red, yeah, it decodes ADR. Yeah, I think it did execute it correctly, at least the second opcode. Yeah, so the bytes are reversed. They are not as they should, I think. Yeah, but yeah, I think we need to swap the bytes. But to make sure, let's just implement it, and then if it passes, great. If no, then we probably need to change the order of the bytes, right? Don't need this comment, right? And then this should increment by 4. And let's implement this. So UDF. So if opcode 1 starts with this, opcode 1 shifted by 4 starts with, I get the amount of ones right. No, I'm missing one. And opcode 2 shifted by 12 equals 1010 triple. Yeah, once we get ESLint, it will make sure we have triple equals everywhere. And then we have IMM. Let's say, yeah, we can do it like they do it in the datasheet, break it into 2. So opcode and F, and then IMM12 is just opcode 2 and F, and then IMM4 shifted by 12 or IMM12. Yeah, that should be the actual value. Okay, yeah. Yeah, that looks legit. And now I think the only thing we need to do, we just need to fix the assembler to swap the order of bytes. So RP2040. No, assembler. and also the, let's open the assembler here and the assembler spec here and UDF.W. And then we can just swap the order of bytes. Hopefully that would be correct. So 4, and this is without any shift, and this is shifted by 12 plus 16, that's 28. And IMM 12 will be shifted by 16. Right, so now we can fix this test case. Assembler spec. Okay, so I think let's remove the test filter. Okay, this passes, perfect. And let's see what's going on with the RB spec. Okay, now it seems to hit this instruction. Oh, and yeah, thank you test case for figuring out that we also forgot to add 2 to PC, right? We do it with the other instructions, other 4-byte instructions. So UDF 2 encoding, yeah, encoding T2. Okay, now it may change to green. Okay, great. So now let's see. I think I have the files from Valerio, so we can now see if this works. Let's try that. I think I extracted, yeah, blink 2 and blink 2. So we have the reproduction. Yeah, I think, yeah, I also changed Emulator run to load blink 2. So this will load blink 2, and then let's start GDB multi-arc. Rapid2040.js, and then bigger font. Then just use the reproduction from Valerio to see if now this works differently. So GDB multi-arc file, GDB multi-arc file blink 2, target remote winhost 333. And we got GDB connected to our emulator, setting up this breakpoint. Let's put this side by side with the emulation output so we can see the result. Yep. And then I think the issue said we should just C N N, and then we should see the unimplemented instruction. Let's try that. So C, continuing, and then N and N. And yeah, it seems like there is an unimplemented instruction. This time it's something different. Ooh, interesting. Yeah, what's that? So yeah, so now we got a different issue. It's different. It's different opcode. What is the address? It's also, oh, wait a moment. This is like in 8682. That was where we had it before, and now it's in 8684. And yeah, the numbers don't look the FFP. So I think I know what the problem might be. Not sure yet, but I have a feeling. So when we have a breakpoint, let me show you that. So when we have a breakpoint, we rewind the PC to the beginning of the instruction just before the breakpoint. And I think we don't do it correctly now, because until now the breakpoint instruction was just 2 bytes, but now it's like yeah, let's check the implementation of onBreak. Is it? Yeah, maybe in the GDB server we implement that. Yeah, so you see we call rp2040.stop and then we remove 2, but in this case we should probably remove 4 because we are going to add this to back again, so PC is now pointing incorrectly, and then probably GDB is just trying to restore what it had in that memory location, but writing other stuff, writing it to the wrong location. So yeah, one way to fix this would be to tell onBreak how much to rewind, even though I think it might be more useful if this was hidden in the inside like the CPU, so inside this class. So maybe add how many bytes to rewind the last break instruction. So just have a variable that will tell us how many bytes we need to rewind, and then we can set it. So in this case, this dot rewind would be 2, and in this case it would be 4. And then we can just do rp2040.break rewind. And okay, now let's check this. Let's retry this and see if now now it works better. So breakpoint set, and now I mean GDB connected. Let's set up the breakpoint and then see, paste, yes, continue, and N. Okay, perfect. No warnings, no errors, and it seems to we are inside malloc. Yeah, it's nice that we can actually see the source code, or at least some of it. And now let me check if things like finish actually work, because in the past, yeah, it seems that they worked. Cool. In the past, whenever I used finish with the emulator, I remember it would just go crazy, and I guess that's one of the reasons. And now, whoa, yeah, well, now we can actually properly debug this this code. Cool. Yeah, I'm just so happy I can do stuff like that. Where are we now? Initialize and destruction function. libc. Ooh, we are inside embed start. What happens if I just continue here? Yeah, we keep breaking at malloc wrapper, but here we go. Hello world. I'm not sure what this program was supposed to do. I haven't seen the source code for it, and I don't think I have it locally, but probably another attempt to debug the cystic thing. Anyway, cool. So I think we can say this issue has been solved, and now we finally have, I hope so, a reliable debugger. So fix rp2040 decoding of the UDF.W or .w. I think that's UDF.W. Yeah, UDF.W. That's the T2. T2 variant of UDF used by GDB for breakpoints. And this closes issue number, what was that? 8. So this is a quick way to close issues from Git commit messages. So let's commit that. Let's just take a look at the changes before we commit to them one more time. So here we did this thing with rewind and the encoding of the opcode, and we know it's that's the test case. And yeah, this is like the funny. I formatted the code so it removed this space. I think it should have happened when this was committed. Anyway, so break rewind 2, break rewind 4. Yep, it's okay. UDF. Okay, seems good. Commit and push, and yeah, one less issue to worry about. Now the list should update to have 5 open issues. Not yet, it's still pushing. All right. Oh, this is one of the longest pushes I have ever had. I wonder if my internet is dead or something like that. Okay, so now we should only have 5. Yes, 5 open. Okay, on to the next one. Yeah, let's take a look at those. So first of all, let's make it more fun. Instead of having like stars, let's have check marks so we can actually check them when we finish them. That will be much more fun to do. Okay. No, that didn't work. Yeah, I should have added, I think this is the syntax for check marks in Markdown, in GitHub style Markdown at least. Okay, update. Yep, now we can check this one because we just did it, and let's do the remaining ones. So we have CMN, NOP, revs, ROR, and SXTH, and then all those DSB and ISB. Let's start with those DSB and ISB. So let's close all these files. Yeah, we actually got this sample encoding we can use. Okay, so yeah, let's get rid of all of these files for now, just cleaning up a bit. And then yeah, we can go to the RB2040, RD2040 spec, and add those instruction, ISB. We had MSB. We had one of them, maybe DSB. I remember, maybe we don't have case for that. DMB, yeah, DMB. Yeah, we don't have test case for DMB, so we can also create a test case for DMB. So let's start with the DMB and then just copy paste it to all the others. Where should we put that? After C. Okay. Let's do those as comments for now, and then should correctly decode the MBSY instruction. All right, and then we have this flashy 16 that should be the encoding for DMB-SY. Okay, and then we just expect PC to increment by 4, RB2040.PC to be this plus 4. Okay, this should be green because we have this instruction. I wonder for this test. It was probably, yeah, it was uncovered. Now it is covered, which is nice. Increasing the coverage, and then let's do the same for DSB and ISB. DSB, DSB, and then this is probably, yeah, the same prefix, F3 BF, and then 8F 4F, so that's for the DSB. And for the ISB, that should probably be the same. So yeah, 8F, then 6F. Then these ones are the same. Okay, just let's move this. Let's write it using the same convention as the other ones. Lower. And same here. Same here. All right. That's DMB, DSB, ISB. And finally, let's move this one to be in the correct alphabetical place. Now we can just implement the decoding. So DSB, let's take a look at the datasheet. DSB, yeah, okay, so this is the high byte, the first byte, I think, not the high byte, the first byte. It's hard, so hard. Yeah, let's start with the second one. Copy pasting is hard, apparently. Well, so again, I think, yeah, those bits aren't important, only the higher ones are. These are like option. So and do it in the VS Code, that would be more efficient. So that's for the second part. Okay, and then the first one is just this. I wonder why they use parentheses here. There must be a reason, but it's not important enough for now to check it. We just want this to decode correctly, so it will never interfere with our code. Okay, saving, and where's the DSB? Still, it doesn't pass. Okay, there is like 4 ones here, and this one also starts with 1. This should be equal to this, because I think we have seen this is encoded the same. Let's double check that this is like 1, 1. Yeah, it looks like this one and this one is the same. Can probably change. Let's just verify that they are equal and we are not making a stupid mistake here. Okay, so this should equal this. Okay, so we can swap this. Where are you? And then probably somewhere here, something. Oh yeah, we should add those extra zeros anyway. Yeah, now it passes. DSBSY. Let's also remove this with, replace this with the hex variant. So just okay, and then we have ISB, the last one. ISB, so I guess the opcode is the same as we can see here. And then the second one, I guess this is 60, but let's just double check so we won't make any mistakes. So ISB, yeah, and then 4 zeros for this option part. Yeah, as a binary. Yeah, that's 60. Fine. 8F60. Cool. And then this passes as well. Right. Another cool commit. One more commit to go to a few more test cases. Decoding for, that was DSB or DMB? DSB. And ISB SY. Right. We can probably mention the issue number. I think it was number 10 or something like that. No, number 9. Okay, and now the fun part where we just check those out. Yep, perfect. Okay, so we are left with a few more instructions, like a few more arithmetic instructions, and then this WFI yield. But you know what? Before going on with that, thinking if we could, no, let's finish them, and then I want to go over this list of unimplemented and try to, I think we started it last time, but you know, try to just remove some of the noise there so we can make sure we aren't missing anything important. I think last time we filtered USB. All right. Let's do this. So I think the next instruction, we have CMN. Let's do NOP because it's probably going to be super easy, and then we can move to the, okay, so I think we'll just do, first of all, the easy ones, NOP, WFI, and yield, because they are just like decoding, and then we'll do the arithmetic ones and get finished with that. So that's the encoding for NOP, and then it just does nothing, so it's super easy to, oh, wait a second. Yeah. Okay, yeah. Okay, let's add a test case. There is a chance, I think it's not the case, but there is a chance that NOP is just implemented as a different instruction. So let's see what happens when we add a test case for it, if it's indeed implemented or is it missing. Okay, should execute NOP instruction. Yeah, so new RP. This test will pass anyway because I mean, we are not asserting on anything here other than the fact that PC has incremented, but we'll have a look if it, we want to use this. Let's just get opcode NOP, which always returns this assembler. And opcode NOP. Yeah. Right. Then we can import it, or we can force it to import it. Okay. Opcode NOP. And then we expect the PC just to increment by, don't need those, 2. So this should pass, even though we don't have NOP, or we don't know if we have NOP. But now if we look at the test, we're not going to see it here, but if we will just focus on this test, we'll be able to see if it gets to the unimplemented instruction else. Yep, instruction is not implemented yet, so we just need to decode it just to ignore it, so we don't get it as noise. There is not really a reason to do it other than, you know, reducing some noise if somebody uses that instruction. So that was, let's just copy it again. Okay, and now we expect it not to execute this code. Oh, it's still green though. Interesting. Could be the reason. Oh yeah, we don't need to shift opcode just to compare this. Let's just console log up and see that it actually runs. Yeah, it now runs, and then this one shouldn't execute. And it doesn't. No more green here. Cool. Next, we want to do yield, and there was another one, WFI. So let's do WFI. Again, super simple. Just copy paste. For now, we'll at some point we will let's do them together. So there is like WFI, and there is also yield. So this is for WFI. And let's add it to the assembler as well. Function opcode. Turn this opcode yield. And yield is just this. Return this. All right. So this is for WFI. This is for yield. They are very similar, but not the same. Right. Cool. So let's just add test cases. From filter. Where is like the last instruction? Here it is. WFI. So opcode WFI, and this is basically a NOP for now, and the same for yield. Yield opcode yield. Okay, and let's import those. Opcode WFI, opcode yield, and this one should be green, and yeah, this is not green. So let's just triple check by console logging WFI, and then, you know, just focusing on this one and see that this executes. Or maybe not. Oh, interesting. How comes? Oh, interesting. It went into subs. Like the same prefix? It doesn't seem so. So why did we go into subs in this case? We are only executing that test. Yeah. Oh. And what's that returning? Maybe we are missing. Oh, wait a second. Yeah, this one seems a bit too short. We are missing something here, like this one at the beginning. Okay, so that's again a good reason to write tests and triple check yourself, because otherwise, okay, so now we should also fix this one, and now we'll probably see it saying, yeah, WFI. So yeah, so I'm so happy we spent like the extra minute to check this, because otherwise we'll just get an error message with whenever we would encounter the WFI. But then Yeah, maybe we should actually keep this print. I think yield, I'm not sure if yield does anything useful. I think it's just a hint for the operating system. Int yield, what does it do? Yeah, no, no explanation about that. Just yield int. Let's see if there is anything here about yield. In the Pi Pico datasheet, yield. Interesting. Didn't know they had this list of all the instruction, or maybe I did and I forgot about that. Anyway, there is node number 1F. Oh, nice. There is a list of cycles for each instruction. Cool. I didn't know we had that list. So funny. We can now count cycles as well. That's cool. I didn't know we could do that. Like make the simulation cycle accurate. That would probably be super slow, but funny that we found that now. Yeah, I see most instructions do take one cycle, other than a few instructions that take more than one cycle, like this is 1 plus n. Okay, cool. Nice to know that. Anyway, so exclude time spent waiting for interrupt or event. So probably it means that yield is waiting for some kind of interrupt or event. So yes, there is no documentation about that. Okay, so if anyone knows what yield should really do, let me know. For now, let's just print yield, WFI, and also WFE. So if we have them in code, we'll know we need to, they are missing, but at least we'll see the instruction name and not just, you know, not see anything and wonder why the code isn't working as it should. Okay, cool. So we added those, WFI yield and NOP, I think, as well. Let's review the changes and commit. Huh? Oh, I probably organized the imports and that's why it sorted them finally. Okay, NOP, WFI yield, NOP, WFI yield, also assembler, and now just run again one of those links that we have to see if they still work. They shouldn't be affected by, or they still don't work. Yeah, GPIO set too high, and now we have the cystic issue, so it will eventually go too low, but not as quick as we would like. Previous one, I think. Let's also test. There was like hello UART. Oh, by the way, I will show you something cool on Wokwi in a moment. Something that I added yesterday, and I think it's pretty nice. First of all, implement WFI, WF. I don't remember what we implemented. NOP, WFI, and deal. It's actually not implement, just decode them. All right. And oh, wait a second. Where does this go? Oh, I think we just reverted it to what it was before. Like we haven't committed it. I thought for a moment we committed the changes here, but apparently we just reverted them to what they were in the last version we committed, preparing for the first alpha release. Okay, so this is done, or maybe let's also add the issue number. It's number 9, right? And I can't really cancel the push, but I will just force push as soon as this finishes. Yeah, and let's do the fun thing of those instructions. Yield and WFI. Oh, it did push the eventually push the modified commit. Cool. So we don't have to force push. Cool. And now before we do the rest, the 5 remaining ones, I wanted to show you something cool with so yeah, we have this like actually we don't need Pi Pico. It's so starting from Wednesday, Pico in the simulator is just enabled, and you can just, you know, run any sketch that you like. And I just added a new feature last night. Let's just increase the font size to make it a bit more visible. So now there is an option to load an hex file and start simulation. So if you have if you compiled your own hex file like we did here, like let's take hello UArt, you can just open it and it will run it in the simulation, or we can probably try one of those blinks as well. Load hex file, and then there was like this original blink, and you can see here the LED blinking. So if you have an X file and you know you don't want to, you just want to play around with it without getting the Raspberry Pi Pico out of your drawer, or you know, setting up the simulator from command line like we do here, you can do it now on Wokwi. Anyways, yeah, a few more instructions to go. What else do we have? We have yeah, the last mile. We have CMN, and then all those revs, ROR and SXTH. Let's start with the assembly. CMN, compare negative. An instruction that nobody uses. Okay. So assembler, you go away, assembler spec, and then let's do okay, so CMN, where are you? CMN, and then let's say, okay, let me show you a cool trick how we get the encoding for this real fast. So CMN, and let's say R5, R6, and then we want to know the encoding for it. And last time I tried to use the compiler, but it didn't work. Apparently that nice guy Graham Sanderson left a comment on YouTube explaining why it didn't work. So if you want, just go to the last live stream from Tuesday YouTube page and then check out the comment that explains. But he explained like there are 2 types of syntaxes: unified syntax and standard syntax. And here they are using the unified syntax, but I'm not sure I remember all the details correctly, but I think GCC defaults to the other syntax, so that's why it didn't work. Anyway, one quick way to get encoding would actually be to just assemble it. Let's see if this works. Yep, this works. And then we can take a look at the assembly code listing. So that's F1 and view compiled assembly code listing, which behind the scenes it runs AVR objdump, and then we can see like this is the assembly code for the machine code for this, the encoding for this instruction. So this should make our life easier with those new instructions, since we don't have samples to test with. And let's encode them. So output CMN, and we expect CMN R5, R6 to equal this. And CMS, guess that's similar to CMP. we don't have assembler for CMP as well. I think was probably one of the first instructions that we implemented, and we never bothered to create assembler for them. Anyway, RM and RN. So there are probably another instructions that take RM, RN. No, that's the only one. RN, oh, N and M, RN. Yeah, just copy this and change the prefix. NM, MN, and this prefix. Okay. And now it's green. Perfect. So it agrees with the compiler. And on to the next instruction. So we had CMN, and then we had rev16 and revsh, right? rev16, revsh. So another RMRD. Let's get the encoding for that. So revsh R2, R7. And let's take a look at the compiled version. So that should be revsh, that was R2, R7, right? And this compiles to this. R2, R7, and revsh, code rev, and then probably it's the same thing, but just with a different prefix. So let's consult the datasheet about that. So RD and RM, and this is the prefix. RD and RN, yeah, it seems good. Removing those spaces and importing. I wish auto imports would just work for functions that we introduce, for new functions. Anyways, what happens here? No, it didn't work. Why is that? I think there is a missing digit. Yeah, missing one at the front. Yeah, that's why we need this to SPODO. So we have revsh as well. Oh, that was revsh or rev16. Yeah, rev16. So test wouldn't help us with this copy paste mistake, because we did the same mistake across the board. But anyway, the next one is going to be revsh. So let's write a test case for it as well. Let's say R1 and R5, R1 and R5, and let's see what's the opcode for that is. Revsh R1, R5, you compiled assembly code listing, and it will probably update in a second or so. Yeah. R1, R5 should equal this, and now we can also implement revsh, and it's probably the same, just different prefix. And yeah, again, it didn't copy the one. All right, revsh is done and it's green, and let's import rev16 as well, so it will hopefully be green as well. All right. Okay, this is green, rev16, and I think we have two more instructions to go, roar and sxth. So roar, I think it's also this one, roar. Yeah, it also has two parameters, so roar. And let's do R0, R6 and R0. Okay, and create this test case for this. Rev16, revsh, and then we have roar with R6 and R0. Roar R6 R0. We want this to equal this one, and then okay, then let's implement it. So roar, and that should go like this: RDN and RM. So RDN, RM, and then RM and RDN, right? MDN. Cool. Oh, I edited the wrong one. Okay, that's in roar. So again, RDN and RM, and in the opcode reversed RM and RDN, and this is the prefix. And finally, let's just import it and see if it's green. Okay, this is green, great. And now for the last one, that was X something. So the last one is SXTH. We have SXTB, so now we want to do SXTH, and let's say we want it with R1 and R6, or let's make it more interesting, R6 and R3. I don't know why that's more interesting. And then SXTH, let's see how the compiler encodes it. SXTH. Meanwhile, we can create the skeleton for the encoding function. SXTH, okay. That's the encoded one, the compiled one. And then SXTH, SXTH, no auto import yet, so let's import it manually. Okay, and then fail because we haven't updated the prefix, so that's the last thing to do. SXTH, and that's the prefix, followed by RM and RD. And again, it forgot to copy the first bit. Okay, cool, this is green, we are done. Hopefully we won't have to touch this file in the near future. Maybe if we, when we tidy up the tests, maybe we'll do it soon. When we tidy up the tests, we'll just, replace all those places where we have those magic constants. And there aren't many of them, but here, like this one, or probably CMP as well. So maybe we'll touch it again soon for that. But other than that, we are done with the coding instructions, and now let's create test cases for those instructions. So there is like a CMN that gets two registers like R5 and R2. Opcode CMN R5 R2. So I think let's see what CMN does. Compare negative. Adds two register values, it updates on the result and discards the results. So how does that work? So it's taking, so there is zero shift, so it takes RM and adds RN to RM with zero shift, so I think it doesn't do anything, with zero carry, and then updates the flags based on the result. So Yeah, I guess if they are like, not sure what's the use case for this. Maybe there is an example. The same as ads, okay, but what is the use case? Why do we need it? My internet is pretty slow today. That's CMP. No idea why we need both of them. And they telling us what they do, but not why to use them. I mean, can just write a test case, but and that's probably what we are going to do. Probably just copy one of the test case. They say it's like adds instruction, so let's just copy the test case for adds adds with to register. So yeah, CMN, and then just copy this test case, other than changing the opcode to CMN, and then R2 with R7, and then yeah, we expect it not to change any of those registers, so R7. Actually, all the flags here are false. I wonder if there is like a better test case that would change the registers. So let's see if there is another one for its reg. Or no, we don't have one that that actually changes the registers. Anyway, CMN. Yeah, I mean, we could probably have something like -2, or we can just force this to be -2 +1, and then the result should be negative. This should be 1, and this should be -2. Actually, we don't need this. It will be automatically convert to unsigned when we assign it, but here we need to convert it to unsigned. Oh, it's 1. Okay, and now we expect the result to be negative, right? So yeah, we haven't implemented it yet. That's why it's red. Adds, and then just copying the logic from adds RB2040 opcode adds. ADDS to registers. That's probably the one. Okay, and then let's add CMN. Let's do the decoding. CMN. RMRN. And This is shifted by 6, this is by 3, and Rn is the lower one, right? Yep. And then we just go away. We don't need to store the value. And green? No, not green. Huh. Why is that? The result is 1. Interesting. Oh, yeah, I can see why. We are adding the wrong registers. It should be R7 and R2 and not R5 and R2. And there is a carry here. Why is there a carry here? Actually, yeah, one cool thing we can probably do is just check the result on an actual Raspberry Pi. Let's try that. I think that would be fun. So this is the opcode, right? 16. So we have the opcode here, 42D7, and now let's just point GDB at the actual Raspberry Pi. That would be Raspberry Pi 333. And now we can do something fun. We can, no matter what the Raspberry Pi is doing right now, or the debugger even running, yeah, it seems to be running. Why is where? Let's don't load this humongous elf file, so maybe it will go faster now. I think it has a problem with connecting to the Raspberry Pi. Maybe this will work. Oh, yeah, target need reset. Probably that's the problem. DB is very slow nowadays. Target need reset. Maybe we'll just restart this all open OCD. And GDB crashes. Okay. New GDB connection. Yeah, wow. Undefined debug reason. Target needs reset. Let's just try to disconnect the Pi Pico from my PC and reconnect it. Maybe that would work. Yeah, it seems to find it again. Okay, perfect. We just needed to physically reset the Pi. Okay, so now we can do something like that. Set PC equals to the beginning of RAM, and then write this opcode. That's the beginning of RAM. 1 extra 0. Write this opcode D2 42D7. Oh, this is slow. GDB is so slow today. Guess there is something wrong with my LAN or something like that. Okay, so now let's just disassembler at this address to verify that we have actually written this instruction correctly. Yeah, we can see CMN R7 R2. That's the same instruction. I wonder why it didn't update PC though. Oh, no idea. Or maybe it did. Okay, let's try to set it again. And then let's set R2 to 1 and set R7 to -2. Wow, this is so slow. No idea why. Do you see and hear me correctly? Because I don't know. I have a suspicion. I have a feeling that my network connection isn't so good if the Raspberry Pi works so slowly. I mean, this is local. Negative acknowledgement, but no packet pending. Okay, let's try to run a single instruction, I guess. And now we should have been, after executing this instruction, and let's print the flags. Yeah, you can see that no, R2 and R7 weren't updated. Or let's try that again. R2 equals 1, set R7 equals thank you, ProteusNet. Nice to see that you are here. Yeah, I don't know. GDB is very GDB on the Pi. It's like working very slowly. Maybe there is like a connection issue, like the wires aren't. I don't know. There is like all those warnings. Let's restart. OpenOCD. Target remote Raspberry Pi 333. Yeah, I don't know. Funny, at the beginning we had this issue where the Pi debugging was super fast, and then our debugging in the simulator was super slow, but now it's just the opposite. Debugging the actual Pi is so slow, and the simulator is so fast. Anyway, this seems like a more legit state. Let's try again. So let's set PC to this beginning of RAM, and then set this, write this instruction 42D7, and then R2 to 1, R7 to -2. And then single instruction, and then it takes forever. And info registers and see what's going on. Okay, so now we can see we got a right value in R2 and R7. They were updated, and we can check XPSR, which is like I think the high, if I'm not mistaken, the high nibble, like this 8 is the flex, right? XPSR, it's APSR, and I think, yeah. So we can see that only N is set here if this test went correctly. So there shouldn't be a carry. Interesting. So maybe we found a bug in, and if we did, it also affects the adds instruction. So if we did find a bug, I'm glad that we ran this test. Okay, so carry is true only if result is greater than FFFFF, and I think it shouldn't be greater. Ooh, yeah, I think it should be greater, not greater or equal. It should be greater because the result is -1 here and there is no carry. So yeah, sure, we just found a very very specific bug. Only if adding two values gives you this -1, or if all F's, then you get carry while you shouldn't get carry. So cool. One less bug to go. I don't know if that would have been that would have done something, but I mean, if that would have interfered with our code in any way, but if it would, then that would be a hard one to spot. Let's just see all the places where we use this, where we have this, yeah, copy paste issue. So I guess here as well, only if it is greater than this, then we had a carry. And then here as well, probably. Here as well, probably. Ooh, copy paste mistake. There. Okay, this not this one is, oh, this is CMN. CMP, and another CMP. Yeah, I hope the other queries are good. Okay, so if any of you have ideas to more kind of tests like this one that we can run on the actual Pi to find if we have some other issues in the logic, then that would be cool. Anyway, yeah, I think, why do we have a core file here? I don't want a core file. Okay, let's not commit yet because we have a few more instructions to implement, but definitely we can start writing the commit message, or maybe yeah, let's just, you know, split it to 2 commits. One commit will just be this without the CMN for a moment, just the bug fix. So yeah, that was the spec file. I want to see this diff. So yeah, fix RB2040 H invalid carry in an edge case. Can still see and hear me, because I think YouTube is telling me there is a problem. Guess not. Range. Yeah, I think I'm back. Anyway, invalid AK carry in an edge case. In case the result was -1, or we set the carry flag incorrectly. Cool. So that's one bug less, and now we can go back to implementing those instructions. So let's push this. So we have the test case for we did CMN, and I think the next few ones should be even faster, because we have the next one is, you can already check this. The next one is like rev, and we already have some variation of rev, so it should probably be okay. Cool. Good to see that the stream is back for everyone. Okay, so there is like rev 16, and what does rev 16 do? Rev 16, where are you, Mr. Rev 16? Byte reverse half word. So just reverse the byte in each half word. So it's like ref, but just half words. And then let's say we want R0, R5. So if R5 is 11223344, we expect it to be 22114433, just reversing every pair. So opcode rev 16 with R, what happened? Oh, rev 16, R0 and R5, RB2040, no, not the spec, RB2040 DS, and rev. Okay, and then we have rev 16, and let's do it. So this is the prefix. Right, and then we just want to reverse each pair. So the high bit will be just the high byte will be just the one next to the high one, and just the same logic as we had. I think oh, wait a second, that's the high one. All right, yeah, now it makes sense. So the high one is actually, yeah, it seems to make sense. We just reverse those two, and then the low one is just by 8, and then the other one is just taking the low byte. Yeah, I think that's fine. So maybe there is 3224. Yeah, 70. Yeah, I think that should be fine. So the result should be in R0. Green yet? Yes, it's green. Perfect. So yeah, I hope I didn't I mean, it seems to pass the test, so I hope my implementation is correct. And let's if you spot any problem here, let me know. I'm not entirely sure, even though the test passes. I have like this feeling that I sort of know what I'm doing, but not exactly. And let's move on to revsh. Reverses this byte order and then signs it lower. So reversing the two lower bytes and sign extending the result to 32 bits. Okay. So test case, let's say 1 R2, 1 R2, so R2 equals something, and then we call this revsh that nobody uses it because we haven't encountered it yet, so it's a useless opcode, but still want to complete the instruction set, so we'll do it. So yeah, so let's see, we are going to ignore, I guess, the higher bytes altogether, and then hey Michael, cool to see you here. Yeah, it seems to pass the test, so it works. Yeah, we have seen so many cases here where the test passed, but we still had a bug, and we even had some bugs in the test. And we have also seen like the case of the carry that we had before, where we had like this test case, but it just wouldn't cover that specific edge case. So yeah, so tests that don't guarantee anything. Not really. Anyway, let's say we have here F0, no, 55 F0. So we expect this to be F055, and then this would be sign extended, so adding Fs all the way. All right, so let's implement this revsh sharing opcode, and this is the prefix for the opcode. Okay, this is the prefix, and then rm rd, and then we have like I think we have like sign extend 16. Yeah, so revsh, we can just swap those 2 bytes here, and then sign extend 16 the result, and it's green, even though there was a syntax error, like the test runner said it's going to be green. It can predict the future. Anyway, seems like we have this one nailed down as well. Cool. So what else do we have? I think we have one more opcode to go. No, 2. We have roar, which is probably rotate right or something like that. Okay, let's see. So roar. How does that work? Roar. Rotate right. Yes. Where is the instruction? Roar. RM, RN, RDN, and yeah, we have flex and all that funny stuff. Rotate right provides the value of the contents rotated by variable. The bits are rotated of the right end to rotated position on the left is read from the bottom byte of a register, the condition flags. All right, so we have a register that says how many bytes to shift, so that's probably RM. Yep, and RDN is the value that we are going to shift. So let's do roar R5 and R3, R5 and R3. Do we have remember we added a console? No, we probably removed it. Perfect. Opcode roar, not roar, just roar R5 R3, and let's say RDN. R5 had like let's say this value of 1, 2, 3, 4, 5, 6, 7, 8, and if you rotate it right, by 4 we would expect the 8 to go to the beginning. So let's R24 registers R3 want to rotate it by 4, and then we expect the result R5 to equal just this. And yeah, let's test it on the Pi before. We also have to check the flags. We'll only have negative flags here. I'm not sure how it works with the carry. We'll have to see how this shift does the carry. But yeah, I can also already see that this is going to be negative because the high bit is set. So let's also add those assertions. So negative yes, 0 not. The overflow we don't know, and carry. Let's see what how this works with the roar. What does it do with the carry? Shift C. If it's roar, then result, carry out, and then roar. What does it return? Result n-1. What is n-1? How many bits? And oh, it's like result, like the MSB of results, because so it seems n is like the number of bits, like 32. So why would anyone be interested? It's probably the last bit that we shifted. Okay, anyway, that should be true then, because this one, this is set. It should be basically equal to the negative flag, if I'm understanding correctly. Anyway, let's run it on the Pi and see if this n and c are true. Then we APSR, how does it work? So c is 2 and n is 8. So we expect this APSR to be A, if this is the case. All right, so let's try this on the Pi, just like we did before. Let's set PC to the beginning of RAM. Oh, set $PC. And then wait for a very long time. Meanwhile, let's print this is hexadecimal. Oh, this is so slow. No idea why. Should be registers. Yeah. Thanks, ProteusNet. That's a good catch. For some reason I wrote here read hooks instead of registers. Wow, this is super slow. Oh, I just had to hit enter a few times. That's the thing. Okay. So setting PC to this, and then setting the value of this address to be the opcode. No, why it is slow? Pi, are you tired today, or like my network that is tired? Maybe it's weekend, so who knows? Now a new line caused it to execute it another time. All right, so set R5 equals to 1, 2, 3, 4, 5, 6, 7, 8. Set R3 equals to 4. And finally, let's also just double check disassemble here. See if the opcode is correct. And then wait 1 year for the result. Yeah, seems good. Roars R5, single instruction, and then should hopefully info registers have this value in R5, and the high flag of the high nibble of APSR will be A, and we know everything is good. And I really hope this will happen, because I don't feel like running this again over this super slow Pi. I think for the next live stream I'm going to figure out what makes it so slow. It wasn't like that before. Okay, so yeah, seems like R5 got the correct value, 8, 1, 2, 3, 4, 5, 6, 7, and then yeah, A, good. Yeah, seems like the test case behaves correctly. R3 was unmodified. We can actually ascertain that as well. R3 is unmodified. Cool. And now let's implement this RP2040, this roar thing. And silence my phone for a few minutes. All right, rev through roar. What's the opcode? Don't need this console log anymore. Or what's your opcode, Mr. Roar? Roar. Okay, this is the prefix for the opcode. Prefix. All right, roar. Cool. So input is register SRM, and then just to rotate it and update the flags. So const result is just input. The input is RM, right? RM, no, RN actually. RM is how much we are going to shift, and RN. The input is registers RN, const shift this dot registers RM. Actually, let's challenge it a bit, because I see it says we are shifting like it takes only the low byte of RM. So, you know, let's just make sure the test covers that. Let's make it shift by, like, let's add some garbage at the beginning, but it should only look at this byte, ignoring this extra garbage here. RM and FF, and then we expect it to have shifted by shift amount, or input shifted by, I guess, 32 minus shift will probably give us the result that we want. And then RDN, I guess here, yeah, RDN nation well is result, and then we need to update the flag. So result, let's 0 or n negative if result and if this high byte is set, and then as we figured out, and I hope it's not wrong, I hope I understood it correctly, same goes for carry. Okay, saving, and it's red. Why is it red? Because this is, oh yeah, we need to convert this to Boolean, so double negation, and seems like it works. My bit rotation algorithm works perfect, so nice. Yeah, I hope I haven't made any mistake. At least it passes this test, and let's, if you spot anything, I'm a programmer, hear my roar, funny. Yeah, no, it would be funny to add this. Anyway, okay, let's see what else do we have here. We have only one instruction to go, sxth, and this should be super simple because we already have sxtb, if I'm not mistaken. It's just sign extend, I think. So let's do sxth r2 r5 and then it should just sign extend, I guess, the value. So here we have like 88,765, and I guess I will check it out. That's our 5, and then the result should just have this sign extended, so all f's. Taking this value, ignoring this, and sign extending it, and let's just double check that this is what it actually does. Yeah, so it's roaring, so funny, by 0 for some reason, not sure why, and then it takes the result, only 16-bit, and sign extends it to 32-bit, so this should be a piece of cake. sxtb, no. Oh, we should check sxth here. Okay, and then sxth, and the prefix is this. And again, this is an instruction nobody really used, so I don't know why we even bother. And then we just sign extend 16, I guess. And is it green? Yes. Yeah, I guess that would work, like shifting left. If it's too big to fit, then yeah, it should be truncated to 32 bits. Let's just I mean, yeah, we get the right result, so it probably works. I mean, if we take this like value and shift 16 bits, we should probably, yeah, just discards. It just uses 32-bit math to do this shift. So it should be F0000. Yeah, and then we may shift, standard shifting it by 16, then the result would be -1, all F's, because we shift and sign extend. All right, arithmetic shift with the sign. All right, okay, so I think this is a great moment because we finally have the complete instruction set, unless I missed something in my review, and it's implemented finally. Complete instruction set of Cortex M0. I mean, we still miss some instructions, but that shouldn't be too bad. And now, once we have this table that we found before in the datasheet, this table, we can also add like cycle count to each instruction. That would be fun. We'll do it in a moment, but first of all, let's feed up 2040, add CMN, and what else did we have here? CMN, rev16, rev sh, ROR, and sxth issue data, and this should close issue number 9, because yeah, okay. Yeah, I have a feeling. Let's just double check this scary thing again. It feels weird to me that it's the same as the negative one. Shift ROR, or no, it was here. Shift ROR. ROR C maybe. Yeah, ROR C. So there is this number and X, and how much to shift, and we assert that shift is not 0. And then if shift is not 0, M is shift mod N, we don't care about it. Yeah, it seems to return the highest, the MSB of the result. So I think it's good. Okay, cool. Here we have those opcodes, and we double check them with the compiler, and also some of them on the actual hardware, so we can commit. That was issue number 9. It feels so satisfying to check this. All right, so let's push this, and what was that table with the cycles? I think we can do this real quick and suddenly have a cycle accurate simulation as well. I think we had, oh, here, there we go. This is the table. So yeah, so basically everything is one cycle unless the table says otherwise. So we can now have like this. Yeah. 2040. Let's have another field called cycles, and have it next to all the registers. Where are they? Like, yeah, cycles 0, and then I think we have a reset method, so we can also have this dot cycles 0, and then in execute instruction we also increment these dot cycles, and for specific instructions like this move PC, where is that move? One updates PC. Move PC RM. Yeah, everything that updates PC seems to take 2 cycles. So RD is, yeah, I think here we can move things to PC. Yeah, I see we have this. So if then this dot PC, this dot cycles ++, this takes another cycle if we move to PC. And this one probably can't move to PC. Yeah, it's just okay. And then we have add to PC. Probably add PC RM. So this one can't really move to PC because it's only 3 bits. Add register. I think it's called ADR, maybe the one that adds to, no, this adds PC to a register. So which variant can add to PC? Ooh, this one seems, yeah. else if rdn equals regpc. What is regpc anyway? 15. Oh, why do we define it here, and how did we do it above in move? We just compare it with 15. That was, we called it PC register. So let's make it consistent. I think that was reg PC. No, that was 13. So this will be PC register, and this is a Raspberry register, and that was 13, not 12. So yeah, now everything is green again. Cool. PC register. So if we are moving to PC register, it's one more cycle. Cool. And then I think all of those are one, so we don't have to worry about all of those instructions. They are fast. Okay, and then we have all those which are either 2 or 1. We'll take a look at them, and same for all of those stores. Push, pop, and B and B. All right. So ISB, DMB, and ISB. These dot cycles. This is like 3 cycles. DMB. DMB is also 3 cycles, and DSB is also 3 cycles. WFE is 2 cycles, and WFI as well, right? Save is 1 cycle, that's fine. Breakpoint is E. Cycle count depends on processor and debug configuration, so we'll assume it's 1. MSR and MRS is 3. So again, CPS, this depends on processor, so we can't really know for SVC for now. Those are all ones, and then we have BL and BLX. So BL is I think 3 cycles, right? So +2. Yep. And BX and BLX is just another cycle. So 2 cycle. Okay, so I think we also finished this table, other than those that are not very deterministic, I guess. And the branch is just, where is this? Yeah, here we go. So a standard branch is just two cycles, or a branch with condition is either 1 or 2, and there is probably, yeah, branch with conditions. So I guess it's 1 if the branch is, it's 2 only if the branch is taken, but let's double check that. So 2 if taken, 1 if not taken. Yeah, so that's for branch. And now we only have those spatial ones. So yeah, so we have push and pop, and oh, there is like pop with PC, which takes longer. So yeah, let's go to pop. There is N. What is N? B and C. N is the number of elements on the list. Okay, so how many registers we push or pop. So this is like for push. So I think we have this loop for all the elements on the list, so we can just this is for push, so each element is 1 extra cycle. This cycles plus, and not sure what is if writing back the address is another cycle? I think no. I'm not sure. I think this is like all the, what is that? What is address? Registers 14. Oh, it's another thing. It's probably the link register. So yeah, we should count it. All right, and then there is like pop. So that was for push, and then for pop we have like let me see, there is one plus yeah, for each element. That's another cycle. And if we have like P is probably PC because we are writing to PC, then it's another 2 cycles. C says it's excluding, yeah, PC or LR. So that's for, oh, wait a moment. In push, we don't need to count for LR because it says it's excluding PC or LR. So we don't need this cycles plus. This doesn't take another cycle. It's excluding just like here. So yeah, I think this is good. And now we have this whole, those are fine. So we have only all those LDRs, which are 201, LDM, and LDM and STM are probably, they depend on the number of registers in the list. So STM. So for each element, this dot cycles plus. And then same for LDM. For each element, that's an extra cycle, right? That was LDM 1N. Yeah, seems so. Okay. And then we have all those SDR and LDR, right? And then we are done with this cycles thing. So yeah, it's either for LDR it's either 201, and SDR it's either 201, and that's footnote A. And it depends where we are using AHP or SCS or to single cycle IO port. So this is depending where we are writing or reading from. Yeah, I guess we can to do it. I mean, it's probably we can add another flag to read and write uint. So tell them to increase the number of cycles depending on the address, or maybe we can yeah, so maybe we can do something like that. If this dot slow write or slow IO address, then increase the cycles by 1. So basically slow IO will return true for addresses that are not in the SAO, I guess. What is SCS? That's the only mention of SCS. Perfect. So I have no idea what is SCS. So yeah. So this is for all these LDRs. All the LDR variants, they have this thing. And then same goes for all the STRs. R STR. All right, and then let's implement slow IO. Address number, and it return true if address is not within the SIO range, because it says 1 if it's to the single cycle IO. So I think we have like SIO start address. So IO if address is within, is not within SIO plus, yeah, I think like, yeah, and I'm not sure if this is perfectly correct, like the datasheet doesn't say a lot about this. Maybe I will open an issue in the Pi repo and ask about it. Let me add it to the small to-do file to ask about this. Ask about number of cycles for LER STR. But the idea here for now, it's still not going to be cycle accurate simulation anyway, because we have other conditions that may, as far as I understand it, that may affect the time it takes to execute instructions that access the data bus, like contentions in case of multi-core operation. But it would give us a rough estimate of how many cycles a piece of code takes to execute, assuming that this table is correct. Anyway, let's quickly review those changes. Yeah, we changed here everything to PC register and SP register. Cool. Yeah. All right. Cycles. Ooh. Yeah, it's not header, it's address. Good thing that I actually I have like 7 error markers here and I just ignore them. Oh, and here we are even missing an S. Embarrassing. Yep. And here the same typo again. All right. So almost green. It's address. Let's see if we have another place where we write address, not address. Okay, cool. So we also fixed a small typo, by the way. RB2040 count cycles or count clock cycles according to, how did we call this table? Probably has a name. No, it doesn't. It does. Table 81 in the data sheet, and that's in page in section instruction set summary. Right. Yeah, it's good. All right, yes, looks good. Right, we have this cycles. Another small thing that I've seen and just bugged me and I would like to fix, it's just one of those comments wasn't in place. Let's see which one. DRH. I remember there was one which was out of place. Or maybe, oh yeah, there we go, this one. just super annoyed me that this one wasn't in its place. Otherwise, they are all there, I think. Okay. That's misplaced comment. All right, one more to go. All right, yeah, I guess time for dinner is coming soon, so we'll just have a quick look at the remaining things to see if there is anything quick we can fix, and otherwise we have oh yeah, we had this one. Otherwise we have the stream on Tuesday as usual, so we can go ahead, and I think I'm not sure if I will have some time to look at the cystic issue. I really want to get it out of the way. I think from what Valerio tried, it mostly works. We just probably are missing something there, or maybe it works and we just don't know yet. Now with a good GDB, with a stable GDB, it will be easier to figure out. Let's take a look at this ASRS thing. So we said that shifting by 0 is probably giving us is probably not implemented correctly. So let's go to the spec file and try to add a spec for this ASR register. I think that was the one, right? ASR register, this one. Oh no, this one was what we implemented last time. So the ASR immediate was the problematic. Let's try to shift by 0, and if I'm not mistaken, this shouldn't do anything like as you would expect. It should just return the same value. So shifting by 0, and yeah, it returns 0, and I think that's an incorrect behavior, and in this case we expect negative to be 1 and 0 to be false, and there is no carry, of course. So I think that's the place where we have a mistake. Let's double check this with the actual hardware. So let's print the opcode and do the same trick like we did before to run it on the actual hardware. So set PC to this value and wait 1 eternity. Yeah, 1013. Set this address to 1013. Set R2 to this value. Execute a single instruction and then info registers, and then 1 eternity later we'll see if it if R3 now has this value, which makes sense to me. Meanwhile, let's assume that the test is correct and fix the test. So yes, I think we shouldn't have this condition. We should just remove it. So if it's shifted by 0, then that would just not do anything. And then for carry, I guess we should just copy this yeah, this logic from here, which we tested probably. And yeah, okay, this is green. Now it passes. And we can see here the result is, yeah, R2 is equal to this after executing this, or probably executing this instruction, just as we expected. Oh, wait a moment. Something is strange. Yeah, we forgot to set R3. Still got this result. Let's retry this 1 eternity later. Oh, now it's finally fast. So R3 should be 0. Oh no, R3 should have the result, but R3 is -1. That's range. Yeah, that's range. Let's just set it to some random value, and then let's double check that we have the correct opcode, even though we should have. Disassemble address. No, it didn't write this to whatever it should. For some reason this didn't work, this set. Oh, wait a second, I disassembled the incorrect address, so maybe it did work. Yeah, now wait one eternity again. Yeah, this seems shift by 0. I guess it's the same as shifting by 32. And then single instruction, info registers to see the result. And now hopefully we should have the value, the same value in R3. And if not, that's pretty sad. All right, let's see. R3, yeah, -1. I don't get why. Yeah, so I think this range. Let's double check what ASRS, what a datasheet. Maybe there wasn't a plugin. Maybe it was implemented correctly and it's just me who decided to pick on it. ASRS shift carry with type ASR. Oh, wait a second, there is also carry that, yeah, this is shift N, and shift N is decode IMM shift. Oh, this is probably something I missed. Code IMM shift. So decode IMM shift with type. What was the type for this? 10. We don't have this decode IMM shift, I guess, here, right? So decode IMM shift 10 if SR type. All right, if it's 0, then 32. Also, so there is like so probably this was correct after all. And wait a second, yeah, press immediate. RP-40 ASRS immediate. So, yeah, I guess shifting by 32 would result in 0, but then why do we get -1? I mean, the pi does something else as well, like it doesn't return 8, it doesn't return 0, it returns all F. So maybe there is another bug here. So if this is 32, the shift amount is 32, but what does shifting by, oh, wait a second, it's shifting 32, but it's an arithmetic shift, so it basically copies this bit all over the place. So yeah, so that makes sense to me now. So basically, if we're shifting this by 0, then the result should be this, and then not sure how this translates to is there any carry here? Shift C, C with ASR, ASRC, and carry out is extended X shift -1. So bit 31, I guess. Bit 31. So that should have carry because the bit 31 is now 1. And let's check what does this say. If it has carry, yeah, XPSR should be A, just like we had before. So yeah, so another small but maybe important bug found. All right, so in this case we should shift by 32, not by 0. And then this is just like, okay, this is correct. Not sure if, oh yeah, just shifting by, I'm not sure how JavaScript works in terms of shifting this value by, let's see how this works. Console log, if JavaScript gives what we want, I think it will just give, just return the same value. Yeah, it doesn't, oh, wait a second, maybe it does. I think it does. No, it doesn't shift it. So basically, if I'm 0, otherwise, if it's 32, we just so if IMM0 is, if the shift amount is 0, then we need to shift it by 32, which means we just take the maybe we can do something like that. Why do we have input? And probably, oh, we do use it. Yeah, interesting. So yeah, so I think we can do something like that. So if we are going to shift by, we are going to shift by, yeah, so first of all, we can write here input. And then if it's 0, then we are just going to take the high byte, the high bit, and then shift it by 31. So copy it all the way. Yeah, now it passes, and I'm just not sure about the carry. Yeah, it seems to be good, I guess. Not sure if this -1 is correct though. Yeah, I think shift -1, yeah. Yeah, I think this might be correct, hopefully. Anyway, yeah, it's pretty much time for dinner now, so I will just commit it, and hopefully this is better than, I mean, this seems better. We have one more test case and we verified it with a Pico, so it seems to be a bit better than what we had before. But if any of you feels like digging it a bit and checking if there is any bug, especially with the carry or something like that, I would appreciate that. Other than that, let's commit and cross our fingers, fix bug in ASRS with 0 shift, and the issue is, I think that was number 10. Yeah, number 12. Fix 12, hopefully. Oh, forgot to save something. Right, now everything is saved, and there is a new test case. Okay, let's push it. And yeah, I think we finished most of the issues. We still have like this. Didn't I close it? Oh, it didn't push. We still have this test case to add, and this setting up ESLint, which we'll probably do in another off the stream or spontaneous stream session, or maybe in the stream, I don't know. We have like, I want to do GPIO this week, and also start working about the multi-core, and there are also requests for PIO, so there is a lot to do. But slowly we'll get there, slowly. But anyway, have a great week, and see you again, I guess, on Tuesday's stream, or maybe even before, if some of you find some interesting bugs that we have to look on during another spontaneous live stream. So, heading off to dinner. Have a great rest of the day. Bye bye to everyone.